Welcome. Today we're going to talk about how to solve a system of inequalities. Just a quick review of some things that we learned in Algebra 1. We're going to extend it just a little bit. Hopefully by the end of this lesson, you'll be able to identify which system or which solutions make a system of linear inequalities true. We are going to first look at a way to solve systems of linear inequalities graphically. Actually, yes, graphically. And to do that, we have a couple of steps that we're going to follow. We are going to graph each inequality, shading the correct area. We're going to identify the region that is shaded in multiple colors, and that will represent our solution set. I think it's important to make sure that we solve for y, if needed, so that our equations are in slope-intercept form. This is how we learn what the slope is and what the y-intercept is, and that's important when graphing. All right, so let's look at an example here. The first example, example 1, has two inequalities that we're going to look at. Neither are in slope-intercept form. Let me see if I can line this up. So I'm going to start just by writing these inequalities in slope-intercept form. The only challenge, or the only thing to remember when solving an inequality versus an equation is that if you ever multiply or divide by a negative, you'll need to flip the inequality. In this case, I just add 3 to both sides, and I end up with y is less than or equal to x plus 3, so no flipping is necessary. I'm going to identify my slope. That's the number in front of the x variable, which in this case is a 1. My y-intercept is 3. That's the constant that's in my equation. And I know from looking at the inequality symbol in slope-intercept form that I am going to use a solid line, and I'm going to shade values below the line. So I have to write this down or I will forget. Solid and below. Even writing it down, y'all, I forget. I look at my next equation. It is not in slope-intercept form either. I'm going to subtract 2x from both sides. So again, no need to worry about flipping. And this is my slope-intercept form. I will offer this one as well. Try to identify the slope, which is -2. And I'm going to identify my y-intercept. I notice for this one that I am again creating a solid line, but I am shading above. So I have all the information I need to represent the solution sets for each individual inequality, and I'm going to do that by graphing both of these lines. If it's been a while, here's a quick review of graphing. I went ahead, I cheated a little bit and went ahead and made some dots on here, because if I don't, I will mess, and y'all don't need to wait while I do that. So my first line has a slope of 1 and a y-intercept of 3. So from the y-intercept of 3, I go up 1 over 1, and it creates this lovely little line, which I'm going to use my geometry shapes to connect. I have drawn my line that we're to use in my inequality. I'm going to label this one so that if there's ever any question, I know which one is which. And I'm going to shade the area below. And my shading is not spectacular. Forgive me. Highlighters work really well here so that you can see overlapping colors. For the next one, I am going to start at -5, and I am going to use a slope of -2, which means that I either go +2, -1, or I could go -2, +1. A negative and a positive remains negative in division. So I'm going to draw a solid line. I am going to go ahead and label it so that if there's ever any doubt, I know which line represents which. Greater than or equal to -5. And now I need to shade this line. This line is getting shaded above. And again, I'm going to kind of sloppily shade this. And hopefully when you do that, you can see that there is a section of my graph that is covered with both colors. It kind of makes almost a green color because I chose my highlighters very significantly. And so any number that is inside this green or this doubly shaded area would represent a solution. Remember, solutions are just ordered pairs that when substituted into my original equations make both true statements. Because I used solid lines, any ordered pair that lies on either of these lines would also represent a solution. All right, why don't you take example number 2, solve the first equation for y, go ahead and graph both, and see if you can identify the solution set. Then we'll check back. All right, here's what I came up with. I took my first equation and I solved for y, identifying the slope and the y-intercept. The second equation was already in slope-intercept form, so I just identified the slope and the y-intercept. Because this is just less than, I know that just a dashed line, and to shade below, for this one it's solid, and above for the greater than or equal to sign. And notice that when I graph my two lines and shade the appropriate areas, there are no points of intersection. Therefore, this system of equation has no solutions. Sorry, system of inequalities has no solutions. That is indicated, or you can see it algebraically by noticing that both inequalities have the same slope and different intercepts. Had the inequality symbols been reversed, there might have been some solutions, but as they are written here, there are no solutions. All right, moving on, let's look at example 3. What I notice about example 3 is that there are 3 equations here. I will need to graph all 3 and find an area, if one exists, that is covered with all 3 different kinds of shading. The first thing I notice in this problem is that there is no y value. And so this is a vertical line. Just a vertical line. And because we are looking for x values that are greater than -3, then when I draw my line, right here, I'm just going to sketch it, I'm going to shade the area that is to the right because I want things that are greater than -3. So it's right and it's solid. The next equation is in slope-intercept form. It is ready to graph, has a slope of 2 and a y-intercept of -3. The third equation is also a special equation. This is a horizontal line. It has a 0 slope until, so its slope is going to be 0, its y-intercept is going to 2, and I'm going to shade below. I'm also going to use a dash or dotted line. All right, so what I would like you to do is pause the video and try graphing these 3 lines and shading appropriately, and let's then talk about what the solution set looks like. All right, I went ahead and graphed more neatly my vertical line, and I shaded in yellow to the right. I graphed the line y is greater than or equal to 2x minus 3. That's this green line. And I shaded above, which in this particular case was a green shade. And then finally, I graphed the horizontal line y is less than 2. I used a dashed line, and I shaded in blue everything under there, except I got to shade the whole thing blue. I did this, wanted to show you this a little bit separately. This is our solution set. It's the area that has all 3 different regions shaded. And just to be thorough, I would shade this. There we go. Now I really have done it correctly. So all 3 regions, this region is represented with all 3 colors. It forms sort of an odd triangle-like shape. Any number that lies in, or any ordered pair that lies inside this purplish area represents solutions to all 3 systems. If the solution lies on my vertical line or on the line y is greater than or equal to 2x minus 3, it is also a solution. If an ordered pair lives on the horizontal line, y is less than 2, it would not represent a solution because that is a less than sign, not less than or equal to. And that is how you can solve systems of equations involving any number of inequalities. And this is actually often used in something called linear programming, which is a application. It's a career that you could go into if you chose to. All right, let's next talk about applications. All right, let's see what we have here. We always start by actually reading the problem. A company manufactures 2 types of printers, inkjet printers and laser printers. The company can make at most 60 printers per day, 60 printers per day, and it has up to 120 labor hours per day available. It takes an hour to make an inkjet printer and 3 hours to make a laser printer. Write and solve a system of inequalities to represent possible combinations of numbers of inkjet and numbers of laser printers that can be produced based on the company's requirements. Whew, that's a big problem. All right, so let's first define variables. And I do that by looking to see what the question is asking me to do. And it's asking me to represent the number of inkjets. So I'm gonna do that. And I make this the X variable or the Y variable will not matter. You'll get similar solution sets. The graph would look a little bit different, but the solution sets would be the same. And then it's asking me to find the number of printers. So I'm going to use that as my Y variable. And now I need to come up with 2 inequalities. I'm using inequalities because it talks about at most and up to. So I could make less than 60 printers in a day, and that would be okay. I could use fewer than 120 hours per day, and that would also be okay. So equality symbols here would not be appropriate. My first inequality is going to involve my counting numbers. So I'm just going to look at things that can be counted. And in physical boxes, at the end of the day, I can have at most 60 printers of either kind, but I can't produce more than that. I have 2 types. I have my inkjet printers and I have my laser printers. And it says at most, which means I could do 60, but I could do fewer as well. So I'm going to use a less than or equal to. For my second inequality, I'm going to make this my value equation. And I'm going to need to use my value numbers. How many hours does it take to make each printer? It takes 1 hour to make the inkjet printers. And I'm going to add to that the 3 hours that it takes to make the laser printers. And I know that at most, up to, I can at most make 120 printers. And that would go right here. That's the most I can make, or the most labor hours I can use. Sorry. The next thing I need to do to find the solution set is to graph these 2 inequalities. So I will need to write them down here. I need to solve for y. And I had x plus 3y is less than or equal to 120. So I'm going to quick solve these for y. Negative x plus 60, 3y. All right, I think that looks right. I'm going to graph these 2 lines. For this one, I notice that it has a y-intercept of 60, which, here, I jumped ahead. I went ahead and labeled the axes of my graph. I put the x variable on the x-axis, the y variable on the y-axis, and then I went ahead and determined what the increments on my graph should be. That having a little bit of pre-knowledge, but I look at my numbers here. 60 is the most I can have in one direction, 120 in the other. So I chose to do it that way. You could flip, you could use different indexing and that would be fine. The next thing I did was I need to graph my lines. So the first one has a y-intercept of 60, has a negative slope, goes down 1/1, and looks something like this. It is a solid line because it is less than or equal to, and I'm going to shade under because I can make fewer printers, but I can make fewer than 60, but I can't make more than 60. For my next line, I am going to start at 40. That's my y-intercept, and I'm going to use a slope of -1/3. And it should give me a line that looks a bit like this. I am going to also shade below here because I can use fewer than 120 hours, but I can't use more than 120 hours. To do a slightly better job of shading. Oh, great. So what you'll notice is that the solution set for this system of inequalities is represented by the green area, or area that has both yellow and blue highlighter. I'm now asked to identify 3 possible combinations that would work. I can choose any combination, any ordered pair that is either on the lines or inside this area. So I might choose to say, oh, I can make 20 inkjet printers, and if I go up, I can choose 10 laser printers or 15 laser printers or 25 laser printers. So I can make 20 inkjet and I could make 35 laser printers. And when I substitute it into my original inequalities, I'll find that the total number is less than 60 and that the man hours required to build them is less than 120. I can also grab, what happens if one day I want to make 60 inkjet printers? So here, if I make 60 inkjet printers, then I've actually maxed out how many printers I can make in a given day. And so that leaves me making no laser printers. I can do the same thing in the other direction. I can say, gee, what happens if I decide to make no ink printers in a given day? 0. Then I can use all 120 hours to make up to 60. Actually, it wouldn't even be 60. It would be 120 divided by 3 because it's 3 hours for each one. I would come up with 40 laser printers. And I can find that by going 0, and I go up to the top of my line, and it's right there, 40. So when inkjet's 0, lasers is 40. When inkjet is 20, laser is 25. I wrote 35, sorry. 35 would also work. And if I make 60 inkjet printers, I can make absolutely no laser printers. And that's how you can use a system of inequalities to solve an actual application problem. I hope you enjoyed the lesson, and we will see you next time.